Boston, Massachusetts. A city strangled by highways, choked by traffic. Through its heart cuts a major artery, plagued by congestion and gridlock. But what if it were possible to replace this urban expressway with parks and send the cars underground? To build a system of superhighways, larger in scale than the Panama Canal or Hoover Dam, beneath the city, without massively disrupting it or shutting it down. Impossible? Or is it? In fact, this engineering feat is transforming America's oldest city, but not without confronting unprecedented challenges. How do you hold up streets and skyscrapers while excavating vast tunnels miles beneath them? How do you design these tunnels to be smart, to handle traffic's deadly fumes or fires? Can cities solve their traffic nightmares by rebuilding their highways underground? The most complex highway system ever built is about to open to the public. Known in Boston as the Big Dig, it's the largest urban construction project in modern history, and its engineering achievements promise to end the city's infamous traffic jams. 8 miles of superhighways, half of them underground, will carry traffic around or below the city.
ILC to Cambridge, members.
But as engineers gear up to troubleshoot the opening, there's one wild card that cannot be engineered. How tens of thousands of harried drivers will react to the maze of changes.
Not too many shy drivers here in Boston.
It's not too bad.
Overseeing monitors in the war room, Glenn Berkowitz ponders the daunting logistics of moving traffic from the old interstates to the new tunnels. To get 200,000 cars underground, major exits, ramps, city intersections, and 11 lanes of interstate highway will have to be radically shifted.
One of the things we're worried about is accidents that could occur where the new lanes take you to different places than the old lanes, and people may not realize that until the last minute and swerve to try to get into the correct exit at the last second, and that could create some problems out on the road.
Never before have such complex subterranean highways been built beneath a city. And opening them to the public will involve one of the most radical shifts in urban traffic ever attempted. The new tunnels will replace Boston's old central artery, Interstate 93. A 40-foot-high eyesore of green-painted steel and concrete. Each day, 200,000 vehicles choke lanes originally designed to carry 75,000. By 2010, planners predicted an urban nightmare of 14-hour-a-day traffic jams unless something drastic could be done. But how could engineers fix or replace a highway so vital to the city without bringing it to a halt? Closing it for any length of time was impossible. But in 1975, Massachusetts Secretary of Transportation Fred Salvucci considered a radical solution proposed by a contractor.
his view was the elevated central artery is like a flashing neon sign saying highways are bad, highways are ugly, highways don't work. We've got to fix this problem at its root by tearing it down and building it underground, and then we can have a good city and a good highway. You know, my first reaction was, this is crazy. You know, we're going to shut the city down for 10 years while we rebuild it. Where's all the traffic going to go, and how can we do this?
Salvucci was obsessed by the contractor's bold idea. As he walked beneath the artery, it suddenly struck him how it could be done. There was enough space to construct a tunnel 10 lanes wide. And if the artery could be supported while a tunnel was dug beneath it, the city could function with a minimal disruption to traffic.
There wasn't another answer, in a sense. The road was beginning to fall down, so it had to be rebuilt. And it'd be absurd to simply strengthen a 50-year-old mistake so it can hang around for another 50 years, polluting and obstructing the economic growth of that city.
Salvucci unveiled a bold plan to rebuild Interstate 93, the central artery, beneath Boston. To reduce artery traffic to the airport, he proposed building a new tunnel under Boston Harbor to extend Interstate 90, the Massachusetts Turnpike, to the airport. But first, Salvucci had to convince a skeptical public that this ambitious highway project would not hurt local residents. He had witnessed the forced eviction of his grandmother and the razing of entire city neighborhoods to build the Massachusetts Turnpike. In the 50s, he'd been horrified by the way the construction of the central artery displaced thousands of families.
We're not taking any houses. We're not taking any jobs.
To win support for the new project, he promised that not a single home would be destroyed.
Fred's kind of unique. An Italian-American son of a bricklayer, an immigrant, who's an MIT-trained civil engineer and has political skills and instincts coming out of his ears. And he is, above all, tenacious. I mean, this guy is the most tenacious, focused human being I've ever met. I mean, sometimes he'd drive me nuts.
In 1987, after years of struggle, Salvucci secured funding for the Central Artery Tunnel project.
A victory for perseverance.
Construction would take a decade and cost $2.6 billion. The rebuilding of Boston's interstates beneath the city would launch the most ambitious highway project in history. But it would be more challenging and costly than anyone imagined. In 1991, the Big Dig began as the largest dredging machine in the world, the Super Scoop, dug a trench for the first tunnel beneath Boston Harbor. 900,000 cubic yards of earth needed to be removed so that pre-manufactured tunnel sections could stretch across the harbor floor. The goal was to pull traffic away from the downtown by giving drivers a second route to the airport. Meanwhile, at a shipyard in Baltimore, Maryland, 12 tunnel sections were being assembled. Shaped like binoculars, each side would hold 2 lanes of interstate highway. In 1992, after a 400-mile journey up the Atlantic coast, the first tunnel section arrived in Boston. greeted by the soaring spray of fireboats. The massive steel hulk was as long as a football field and weighed 15,000 pounds. Over the next year, 11 more tunnel sections would arrive. They would be docked at a ferry terminal where workers would add 25,000 tons of concrete and steel to transform them into interstate highways. Every ounce had to be measured so that engineers would know the exact weight of each section once it was finished. The concern was to keep them balanced so they wouldn't capsize in the harbor. By the time the roadbeds were completed, each section weighed as much as a World War II battleship. In 1993, a barge towed the first submerged tunnel section towards East Boston. Here, the land tunnels for Interstate 90 were being dug to the edge of the harbor. Engineers needed to place the marine tunnel within a fraction of an inch of its land-based partner. But could they do it? In the harbor's murky waters, divers could barely see the huge structures.
They were difficult to maneuver. No one was sure exactly if they were going to get within the fractions of an inch they needed to. They used global positioning systems, satellite information. They shot a laser from South Boston to East Boston to get the exact center line of this deep underwater trench.
At 100 feet below the surface, it would be the deepest tunnel connection ever attempted. If the sections were not aligned correctly, divers wouldn't be able to couple them together to create a watertight seal. As each tube was lowered, the same exacting process would have to be repeated until the harbor was crossed.
What's amazing about this is that these 33,000-ton tunnel sections in a harbor where you can't see more than 2 feet in front of you are lowered down in position and come within a 1/16 of an inch and finally make the connection.
By the summer of 1995, workers could walk unobstructed through the 3/4-mile-long tunnel crossing beneath Boston Harbor. Named after Ted Williams, a Boston Red Sox legend, the new tunnel opened in December, on budget and schedule. It was a feat that would not be repeated again. Enormous challenges loomed on the horizon. To connect the Ted Williams Tunnel to Interstate 90, engineers needed to build a 10-lane highway beneath Boston's Fort Point Channel. That would mean crossing over a subway, past the city's largest factory and post office, and beneath its commuter rail lines.
As if that weren't complex enough, it also happens to be the location where the weakest soils exist in the entire highway alignment to the greatest depth. And that's where we have to put our tunnel.
The huge highway tunnels could not be supported by the weak clays found around the channel. If engineers couldn't find a way to strengthen the water-saturated soil, construction would be impossible. After weeks of searching, they found a solution, 6,000 miles away.
In Japan and Asia, where there is such a land crunch, they have developed ways and economical ways of reclaiming weak land area with a technique called soil mixing, where you use the existing soil in place, but you mix it with cement.
engineers decided to strengthen 750,000 cubic yards of land. Gigantic blades penetrated 130 feet deep into the channel's earth and mixed it with cement. It would take 3 years before the ground would be hard enough to support the excavation of one of the world's widest tunnels. Meanwhile, a new obstacle loomed. The channel's low bridges prevented the tunnel sections from being built off-site and floated in. Engineers warned Salvucci the problem seemed insurmountable.
My first reaction was, we've done an environmental impact statement. You did the analysis that said this was the right way to do it. We've gotten all our approvals, we've got our financing, and now you come and say you don't know how to build it. That's just unacceptable. You have to solve this problem. And it seemed like about 2 weeks later, Lou Solano comes in with this brilliant solution, which is essentially like building a ship in a bottle.
Solano proposed digging a basin on the bank of the channel and using it to construct tunnel sections. Once built, the basin could be flooded and the sections launched into the channel. But because of their huge size, they could not be built all at once.
You have to realize that these tunnels are maybe 90 feet wide and 40 feet deep and 300 feet long. So they're big monsters. They're not small. And that always presented a problem because I couldn't get all the tubes cast in one shot. But the idea was appreciated by Fred because now we had a way of putting in a tunnel.
Workers dug a 1,000-foot canyon, long enough to hold the Empire State Building without its antenna. At one end, 6-story high temporary dams held back the waters of the Fort Point Channel during construction. The basin, 300 feet across, was wider than the largest locks in the Panama Canal. Inside, workers began building the first 4 tunnel sections. The largest would weigh 51,000 tons, more than the Titanic. Each day, mammoth cranes lowered equipment to the bottom of one of the biggest job sites in the country.
Inside of this huge casting basin, it was like a village. The joke was it takes a village to build a highway tunnel here. They had trades from carpenters to iron workers to pile drivers to crane operators, all operating inside of this casting basin. One contractor said it was the largest hole for construction he's ever seen in his life. It was remarkable.
Tons of concrete were poured into the basin to form the highways. Every ounce was carefully weighed and recorded. If the box-shaped sections were too thick or thin, they might not float correctly when launched into the channel. While the tunnels took shape, engineers pondered another potential problem. Would 100,000 tons of highway crossing 6 feet above Boston's red line pose a safety risk?
If one of the concrete tubes got loose and fell directly on the red line, what would be the problem? The problem would be you would flood downtown Boston.
To keep the ocean out of the interlocking subway system, the project installed watertight doors in the red line that could be slammed shut if construction breached its tunnel. To further protect the subway, they began to drill into the channel's bedrock to build 110 concrete columns 6 feet wide. The pillars would straddle the Red Line and form a protective underwater bridge to support the new highway. As the tunnel sections neared completion, engineers prepared for placing them in the channel. The plan was to seal the sections and launch them like ships. But given their odd shapes, would the same laws of physics apply?
People think that ships will capsize in rough seas, but a badly designed ship can capsize just as well in calm water. And so there were a lot of things to worry about. The first one was simply when the casting basin was flooded, would they float? And that doesn't sound like it's a very complicated thing, but they had to float with the tunnel sections almost entirely underneath the water.
The test came in 1999, as the casting basin was flooded for the first time. Time-lapse photography collapsed the night and day ordeal into seconds.
These tunnel sections were massive, and it was quite a sight to see them actually come up from the bottom. It's like a football field floating up to the surface, and there was a lot of issues on whether we had the right calculations and whether it would actually come up as planned.
To everyone's relief, the 27-foot-high sections floated only inches above the water's surface. By keeping them submerged, it would take less weight to sink them once they reached their destination. 2 sections would be moored in the channel and placed at a later date. Amazingly, the other 2 that would be sunk had the additional complication of being weighed down with ventilation buildings sitting on their roofs. Divers helped the engineers guide them into place.
All right, Johnny. We're going to head out to the alignment bracket. You know when you get there? I'm on to the alignment bracket.
As the tunnel sections came closer, they had to let the engineers and the topside people know exactly the location, how far apart they were. We were basically their eyes underwater.
If you remember, there are columns set down into the bottom of the 4-point channel that these immersed tubes have to be floated over and then fit down exactly on top of these columns, very much like a Lego block. But control is critical because once it's in place, we can't get it off again. So we have a 1 chance for success.
Once the tunnel section was in its correct position, engineers waited for the low tide. As the sea receded, water was pumped into tanks inside the section to sink it.
Roger, 2 to touching.
Once that tunnel section come across and we had a diver go down and take a look and tell them that everything was fine, we knew we did the job right.
With half the underwater tunnel completed, the casting basin was drained so that the last 2 tunnel sections could be built. Engineers now turned their attention to constructing the last missing link of highway to connect the tunnel beneath the channel to Interstate 90. To do this, they would have to dig beneath the city's commuter rail lines, carrying over 100,000 people a day.
One of the biggest challenges is the daily train moves. We have commuter trains, Amtrak trains taking you from city to city. We could not interrupt the tracks. We need to keep those 250 moves going a day.
The site posed another problem. Just like at the edge of the Fort Point Channel, the soil beneath the tracks was too soft to tunnel through. But how could it be strengthened without disrupting New England's train service? The contractor proposed a radical solution. Freeze it. 2,000 pipes were inserted around the tracks and filled with salt water chilled to minus 30 degrees. As the liquid circulated to a cooling unit, it pulled heat out of the ground. Within months, the project had created the largest iceberg ever made by man. With the ground hard enough to support construction, workers began digging massive pits beside the site. The plan was to build the sections and then push them beneath the tracks, using an innovative technique called tunnel jacking.
Once the concept was there, then we had to work out the details. Can it be done? Are we going to risk having a soil collapse? Are we going to drag the rail tracks with us as we push these tunnels underneath? And how much force do you actually need to push a concrete tunnel the size of a high school gymnasium through the soil and under the rail tracks?
Tunnels had been jacked beneath other sensitive sites, but never on this large a scale. To protect the train tracks, engineers needed to keep the ground beneath them from being dragged along with the tunnel segments. They decided to pull steel cables in the opposite direction of the jacking to counter the friction and keep the earth in place. Inside the 300-foot-long concrete boxes, welders prepared traditional coal mining machines to grind a passage beneath the tracks. Surprisingly, it was easier for steel teeth to gnaw through frozen earth than be mired down in soft, muddy soil. Tractors quickly scooped up the frozen dirt and rushed it to the end of the pit, where giant cranes hauled it out before it melted. Once the machines had dug a cavity, jacks with a pushing capacity of 10,000 pounds per square inch forced the 35,000-ton box forward at an agonizingly slow rate of about 3 feet per day. It took 3 years to squeeze 3 tunnel sections beneath the tracks, but the ground above remained frozen in place. Just as it seemed victory was at hand, catastrophe struck. 50 feet below the Fort Point Channel, water began to seep through a seal where the land and water tunnels met.
We were manning the site 24 hours around the clock, and at 3:30 was high tide. I went off to check the site, and at that point in time, I had noted it just blew.
$70,000 gallons of seawater per minute poured into the construction site. The pumps were overwhelmed. Divers struggled to identify the problem.
By the time they got mobilized and everything else, the water started to flood the tunnel, and just before 5 o'clock it started coming into the casting basin, filling the casting basin up. It was just overwhelming. We just sat there and watched the water come up.
As expensive cranes sat underwater, managers calculated that the Big Dig schedule had been set back months and millions of dollars.
It's kind of like hit right in the pit of the stomach. After working this long, many of us have been here 8, 10, 11 years, and then you see the water just bubbling in on the backside of a structure you just placed flawlessly. It hurt.
Within weeks, the leak was located and filled with concrete. The dream of linking Interstate 90 to Logan Airport was now within reach. Yet construction of the 1,600-foot-long tunnel cost $1,500,000,000. Hailed as a technological triumph, it's the most complex and expensive highway per mile ever built. Meanwhile, in downtown Boston, engineers building the tunnels beneath Interstate 93 were struggling with an entirely different set of challenges. Before the digging could begin, Boston's 300-year-old infrastructure needed to be moved. Water, sewer, and gas pipes, electric, telegraph, and phone lines all had to be relocated. But where?
It would be very fair to say that it is as crowded beneath the streets of the city of Boston, any city for that matter, as it is above the streets. Peel off the pavement, there's barely any room for dirt under there. It's pipe against pipe, it's manhole against manhole, it's system against system, and it's literally a spaghetti bowl.
They were all over the place when we started. In fact, in Boston, we're legend for not knowing where they are. We might know what street they're in, but we don't get any closer than that. So our plan was to relocate them all ahead of time, put them in corridors where we'd know where they were. And they basically served as another constraint, because that neat corridor where we want to put it, that's already filled with utilities.
Once a path for construction was cleared, the arduous task of digging beneath the city began. Each day, Bostonians awoke not knowing what new detours awaited them. Although the road shifted, at least they remained open. Few realized as they crossed the streets, the ground was actually being hollowed out beneath their feet. At the height of construction, 4,500 hard hats besieged the city. Workers joked that building the Big Dig through downtown Boston was like trying to build the Panama Canal through New York City.
I don't think anyone's tried to tunnel under a city quite like this before. I mean, certainly we've tunneled under cities. Subway lines get built under cities all the time. But this is not just a straight tubular tunnel with a subway in it. This is 8 or 10 lanes of interstate highway on a curving alignment. I mean, it was almost a ridiculous thing to attempt. In fact, it's so complicated.
One of the most difficult engineering decisions facing the Big Dig was how to bury Interstate 93 beneath the city's busiest intersection. Here, thousands of pedestrians poured out of commuter rail and subway lines into downtown Boston. But the challenge of keeping the human traffic flowing paled in comparison to the obstacles underground. Beneath the street, there was a pedestrian passageway, a new bus service to the airport, and the Red Line trains carrying over 200,000 people a day. 93 North had to be buried here. But where?
The only option was to go below the station. That required that we drop the highway down approximately 120 feet and create a tunnel under the tunnels while holding up the Red Line station complex.
But how could engineers support the existing tunnels above while excavating a superhighway beneath them?
Our people came up with the idea of going down with two shafts on either side of the station and then tunneling underneath to build a bridge.
Tunnel workers piled into cages and plummeted into the cold depths. 120 feet below the Red Line, they carved two access tunnels. From here, they would harden the ground for construction by injecting cement grout down to bedrock. Once the soil was strengthened, additional shafts were dug to form two walls 100 feet long. With the side supports in place, a new series of tunnels were carved to form a roof, just 36 inches below the speeding trains. Yet this gigantic underground bridge would protect the new highway passing beneath it. As the tunnels beneath Boston took shape, engineers struggled over how to connect them to the elevated highway across the river. To get 10 lanes of traffic in and out of the new tunnels, they would have to replace a dilapidated double-decker bridge only 3 lanes wide.
So we studied every imaginable type of bridge for that crossing. We went from A to Z. You know how many that is? In schemes and reports and whatnot.
To complicate matters, the old bridge was still needed to carry traffic, so the new bridge would have to be built around it. To cope with the site's complexity, architect Christian Menn proposed a new scheme, a single cable bridge that would be both slanted and asymmetrical. To accommodate more traffic, 2 extra lanes would hang off one side. Named after civil rights activist Leonard Zakin, the new bridge would become a symbol for Boston's renewal. In order to carry 10 lanes of traffic in and out of the I-93 tunnels, it would have to be the widest asymmetrical cable-stayed bridge ever built. To withstand the enormous stress, the cables had to be specially designed. It would take winds over 400 miles per hour to snap a cable, or an earthquake of 7.9 on the Richter scale to topple either the bridge or the tunnels below. Ironically, it was not a catastrophic event that worried the Big Dig's engineers, but an ordinary accident, especially one that might cause a fire. To anticipate this danger in the tunnels below, 7 ventilation buildings were constructed as the first line of defense. "140 fans would blow fresh air into the tunnels and pull exhaust out, changing the air in minutes." But could this ventilation system, the largest in the world, truly handle a fire? Engineers needed to be certain.
We were faced with an absolutely enormous tunnel job that didn't have specific codes to address. I mean, you have codes that tell you how to build buildings and what the minimum requirements are for highways, what they are for bridges, but there are no minimum requirements for tunnels.
To design an effective ventilation system, engineers ignited over 90 test fires to study how airflow fuels or starves flames. The results led to a computerized intelligent highway system designed to handle emergencies. Before long, the system faced its first crisis in the Ted Williams Tunnel, already opened. Elevated carbon monoxide levels warned that traffic had stopped. Cameras located a smoldering bus in the westbound tunnel. Luckily, the passengers had fled. As alarms were activated, flames engulfed the bus. Computers identified which of the tunnel's 24 fans should be pushed to maximum velocity to force smoke and heat away from cars trapped behind the bus.
The fire was pushed from the back of the bus forward. It wasn't just the smoke that was being pushed. You have to note that it was also the heat that was being pushed away. And that's what we were looking for. Once that happens, my worries are gone because that's now a controlled fire. So I realized I was watching the maximum test for this tunnel.
An hour later, emergency teams extinguished the fire. No one had been injured. The intelligent highway system had performed brilliantly, permitting the tunnel to be quickly reopened. On January 18th, 2003, press and fans of the Big Dig gathered to celebrate the first of a series of openings for the I-90 and I-93 tunnels. As crowds look on, managers get ready to reveal the sign for the westbound Interstate 90 tunnel. The tunnel once flooded with water beneath the Fort Point Channel. Its unveiling signals that the final piece of Interstate 90 is now officially open, connecting Boston, Massachusetts to Seattle, Washington, 3,462 miles away.
We've improved the transportation network to one of America's principal cities. We've improved the transportation network for the northeast quadrant of the United States. And we've also provided an opportunity to get so much more, the parks in the city, the reconnection of neighborhoods. All of that is amounting into quality of life. And this project is going to deliver on all those fronts for this city for decades to come.
But the night is far from over. To open up the eastbound side of the interstate, officials must take the rare step of first shutting it down. a race against time, crews hurry to change signs, place barriers to guide traffic, and clean up the last construction debris. By 7 a.m., the interstate must be reopened to the public.
Wake up, Boston. Life just got a little easier. The new I-90 tunnels of the Big Dig are finally open and traffic looks good.
The true test comes on the next morning's rush hour. Despite weeks of publicity heralding the tunnel's opening, some drivers seem to have ignored the signs and are swerving at the last minute to get into the correct lanes. A few even dare to back up. Although the ride isn't smooth for everyone, drivers headed to the airport should find their commutes drastically shorter.
Could have saved maybe an hour, but probably about 45 minutes.
It was great. It was just like, we just flew in. It was so exciting.
I couldn't believe the time we've saved. We've always complained on how much money it cost, but I'm beginning to think it was worth every penny.
Burying highways is only one part of the Big Dig. 3 miles east, Bostonians can glimpse how the project is reclaiming precious land. Spectacle Island was once a toxic, smoldering trash dump, strewn with glass that glinted in the sunlight. For years, its hazardous waste seeped into Boston Harbor. Now, with the dumping of almost 4 million cubic yards of dirt from the Big Dig, this environmental disaster is being turned into a national park with miles of hiking trails.
This is the first wrong that's been righted on the Big Dig. And it's a great sign of things to come, because there are going to be 26,000 trees and plants taking hold out here on the island alone. In the downtown, there'll be 5,000 trees. It's hard to imagine, but trees, plants, open space, grass, it's all coming to the downtown, and it's going to be spectacular.
The true test for Boston's Big Dig will come when the entire project is finished. The elevated highway will no longer divide the city from its waterfront. Its ugly green scar will be replaced by 300 acres of new parks and plazas. The traffic snarls that have plagued Boston for decades will be history. But will the Big Dig be a model for other cities, or a cautionary tale?
Well, I think it's both. I mean, is it a model for other cities? It is, in the sense that we've attempted now to repair the damage done by very poor planning years ago. But it should have taken much less time, should have been much less costly.
By the time the elevated artery is torn down, the Big Dig will have cost U.S. taxpayers almost $15 billion. 70% of the increase is due to inflation and the price of protecting the city's homes, businesses, and environment.
Nobody in 10 years or 5 years is going to remember the cost. They're going to look at this thing and say, what a beautiful job. In my estimation, I've been basically doing engineering for 52 years. I think it's probably the greatest civil engineering project ever attempted.
It remains to be seen how the Big Dig will truly impact Boston. But with half of its traffic now underground, the city's future looks brighter.